Okay guys, today we'll talk about tolerances and types of fits. Regarding the tolerances, the permissible deviation for specific variation in size and geometry. As I told you, we have two types of tolerances. The first one talk about size, second one talk about geometry. Size like height, length, diameter, radius, and so on. Geometry like perpendicular, parallel, concentric, and etc. Size tolerances limits specifying the allowed variation in each dimension like length, height, diameter, and should be given on the drawing. As you see in this example, 40 plus minus 0.1. That means the tolerance how much? 0.1 plus 0.1, which is the range 0.2. Okay, or plus minus 0.1. Yes. That means 20 plus 0.1 acceptable, or 20 minus 0.1. This is the range from 2. From 20 minus 0.1 to 20 plus 0.1. Okay? And the second type, guys, geometrical tolerances allows for specific of tolerance for the geometry of a part separate from its size. As example, this example. See, this is a symbol for geometric tolerances, guys. Inshallah, next class we'll talk about geometrical tolerances. Today we'll talk about size tolerances. Why is tolerance necessary? It's impossible to manufacture a part to an exact size or geometry. As I told you, when you want to manufacture or make a shaft with length 10 centimeter, no one can give you exactly 10 centimeter. So you are the designer, you have to indicate how much tolerance acceptable. If the dimension within this tolerance acceptable. If the dimension outside this tolerance, the part should be rejected. Why? Because it depends on functionality of the part, it depends on the material properties of the part, mechanical properties of the part, and so on. Since variation from the drawing is inevitable, the acceptable degree of variation must be specified. Machine performance, it depends on the tolerance specified for its parts, particularly those that must fit together. When you have two parts and the two parts should fit together, you should take care about dimensions of each part. So you can easily later, after manufacturing, you can easily assemble them together without any difficulty. Small variation will affect the cost of the part. When the variance or the tolerance is very small, that means you will use special tools, special machines, and skilled person to produce the part, and this will affect the cost too much. And also, when the tolerance value it's very, very small, that means you reject many parts, and this will affect the cost also. Functionality, when you assemble the parts. Interchangeability, guys, when you want to replace one of the parts, the replacement should have same dimensions, should fit inside the assembly with same functionality, same properties, so it will be within the tolerance limit. The relationship between functionality and size or shape of object vary from part to part. Now let's talk about size tolerances. As we said before, guys, tolerance is the permissible deviation of dimension from the specified basic size. My question again, who will specify the basic size? Designer. Very good. In this example, designer will draw the multi-views with dimensions and also with tolerances for dimensions, very important dimensions. Maybe this length is not important. Is it 4 or 4.5? No need to put or write the allowance, how much the tolerance here. But regarding the whole size, it's very important. Maybe other part will be fit here. Maybe a screw will be fit here, guys. So the dimension, which is diameter, should be provided with the tolerance. So the tolerance here, guys, it is 1 plus 0.1 minus 0.3. See, the upper limit and the lower limit not same. That means, guys, 1.1 acceptable, 1.05 acceptable, 1.2 rejected, 0.7 acceptable, 0.8 acceptable, 0.65 rejected. So smaller tolerance can be achieved for smaller dimensions, and same thing, larger tolerance for the larger dimensions. It's the designer responsibility to set the tolerances at the highest possible level that result in satisfactory operation of the machine. So your mission as a designer to put the tolerance as large as possible to give the manufacturer flexibility to make the part. Guys, how we can write the tolerances? We have the first example, limit tolerance, by writing the limits, the upper limit and the lower limit. So this length, the dimension is 1, maybe the basic size is 1, but the upper limit is 1.251 acceptable, more than this one not acceptable. The lower limit 1.247 acceptable, less than this number not acceptable, between these acceptable. Plus minus tolerance, yes.
How do you know how much we set the tolerance?
The designer set the tolerance. Actually, I told you when you set the tolerance, you need to know how the part will function. Second thing, what are the mechanical properties you want? Stress, deflection, length, whatever, okay? And also how you will assemble the part in the machine. So at the end, you have many factors affecting the tolerance value. And by the way, guys, not our mission today, how we can select the value. No, how we can write it on the drawing. And second type, plus minus tolerance, as you see, unilateral tolerance, 1.25 plus minus 0.01. Deviation is only one direction from the basic size. As you see, the lower limit, nothing. That means the minimum dimension acceptable is 1.25 exact. The maximum one, 1.25, 1. And bilateral tolerances, 1.25 plus minus 0.003. Guys, again, how much the tolerance value here? It is 0.003 plus 0.003, which is 0.006 unit. The total tolerance is the difference between the maximum and the minimum permissible dimensions. These tolerance values indicate the MMC condition and the LMC condition. What are these conditions, guys? The MMC, it is the maximum material condition, the heaviest assembly. The LMC, the least material condition. Okay? So MMC, maximum material condition, and LMC, least material condition. Now, guys, how we can write the tolerance? The first thing, specifying dimension tolerance for a part is to decide the basic size. As I told you, it depends on the designer calculations. The dimension to which tolerance are applied, as you see, this is the basic size, 40 as example from the equation in design, assembly, functionality, everything. And this is the permissible variation. You can write it like this or like that or like that. It's up to you. The analysis of strength, deflection, or performance of the part determine the nominal or minimum size required. The tolerances must ensure that the components fulfill its function also, but it should also be as large as practical to permit economical manufacturing. Special attention should be paid to the features of a component that mate with other components when you have assembly. Where no other components mate with certain feature of a given component, the tolerance should be as large as practical so that the manufacturer can produce it with basic machining, molding. And you know that these basic machining and molding not cost like precise processes. Allowance, guys. What is the allowance? So, guys, again, what is the tolerance? Tell me.
The allowable permissible
deviation from the basic size. Very good. Now we'll talk about a second term today, allowance. The term refers to an intentional difference between the maximum material limit of mating parts. Maximum material limit. So when you want to calculate the allowance, you will check the maximum material condition for the mating parts. For example, positive allowance for a whole shaft pair would define the minimum clearance between mating parts from the largest shaft mating with smallest hole. I will explain it later, guys, okay? A negative allowance would result in shaft being larger than the hole. When the shaft is being larger than the hole, that means the shaft will interfere with the hole. How you can assemble them together? Using pressure or sometimes heat with pressure. So the allowance, guys, it depends on the maximum material condition of the hole minus the maximum material condition of the shaft. The third term, guys, again, what are the allowance? What's the allowance? Sorry. Difference between the maximum material conditions of emitting parts. Very good. What is the tolerance? The allowed deviation from the basic size. Very good. What's the allowance? Difference between the maximum material condition of mating parts. Now clearance, guys. The third term, clearance. Clearance is defined as the loosest fit or maximum intended difference between the mating parts, and it depends on the least material conditions. Too small clearance could cause seizing. Conversely, too large clearance would reduce the precision of the machine and affect the lubrication. So again, clearance, it depends on the LMC condition. It means LMC for the hole minus LMC for the shaft. Fit. This is the fourth term, guys. Fit. The term usually refers to the clearances that are permissible between mating parts in a mechanical device that must assemble easily, guys, and that must often move relative to each other during normal operation of the device. So when you fit parts together, you have to think about the assembly. It should be easy, and the movement of the parts relative to each other should be also easy, and think about lubrication also. I see in this example we have a shaft, we have a load on the shaft go inside bearing, and the bearing fit to the body of the part or the bearing holder. So between the bearing and the holder there is some clearance. Between the shaft and the bearing, sometimes clearance, sometimes interference. So transition and so on. I will explain everything later on, guys. So guys, mating parts again. As example, in this example, you have a shaft, we have a bushing, we have a pulley. Shaft must have a clearance fit inside hole bushing. So you can easily assemble the shaft inside the bushing. The bushing must have a force fit inside the hole of the pulley to keep the bushing and the pulley rotate at the same speed or together. So guys, again, basic size, the size to which tolerance are applied. Allowance, the minimum space between two mating parts based on the maximum material condition. Clearance, the maximum space between mating parts. It depends on the least material condition. In this example, we have a shaft. Shaft dimensions given, as you see. 1.247 is the smallest diameter. 1.248 the largest diameter. And this is the hole, guys. The hole size, the largest size or the largest hole, it is 1.251. The smallest hole it is 1.250. I'm talking about diameter. Let me ask a question, guys. Regarding the shaft, which is heaviest? The shaft with 1.248 diameter or 1.247 diameter? No, not same. The largest shaft heavier than the smallest shaft or opposite, guys? The largest shaft heavier than the smallest shaft. That's right? That's right? The largest shaft. No.
No, this is the smallest shaft because smallest means a lot of material.
I'm talking about the shaft, not the hole.
Yes, whenever the hole
Regarding the shaft, the largest shaft is the heaviest. That's right? You have a cylinder with diameter 5, cylinder with diameter 3. Which one is heaviest?
depends on the material. I will tell you why.
It depends on the material. Same material. ها.
بقول لك بالعربي معلش دلوقتي لما يبقى التخن بتاع 5 تمام فالحديد ده قليل بس لما تبقى 3 فالحديد كده تكتب.
You are talking about the hole, not the shaft. This is the shaft, guys. This is the hole. Okay, now regarding the hole, see this body with the hole, okay? Now, the largest hole, it's 1.251. The smallest hole is 1.250. Which is heaviest, the largest hole or the smallest hole? The smallest hole, the opposite. So, I mean, guys, the maximum material condition for the shaft is the largest shaft, while the maximum material condition for the hole, the smallest hole. That's right? Okay. The least material condition for the shaft, the smallest shaft. The least material condition for the hole, the largest hole. Because you are removing more material, will be lighter. Very good. Now, guys, if you want to calculate the allowance, guys, it depends. Ask yourself, it depends on the MMC or LMC? The allowance, MMC, maximum material condition. So, it depends on the maximum material condition for the hole minus the maximum material condition for the shaft. Okay? So, first thing, guys, what is the shaft tolerance? It's the largest diameter minus the smallest diameter, which is 0.001. What is the hole tolerance? The largest diameter minus the smallest diameter, which is 0.001 same. Okay. How much the allowance? It depends on LMC or MMC again. MMC. It's the MMC for the hole minus MMC for the shaft. The maximum material condition for the hole, guys, it is the smallest hole, 1.25. That's right? While the shaft, the maximum material condition for the shaft, the largest shaft. So, when the hole, the smallest hole, minus the largest shaft, positive, what that means? Guys, listen to me. The smallest hole, the largest shaft, still we have a gap in between. That's right? This is the meaning of the plus sign. So we got here 0.002. That means even when we have smallest hole and largest shaft, still we have a clearance. Still we have a clearance in between. We have a gap in between. Okay? Now, what is the maximum clearance? The maximum clearance, guys, it depends on the LMC. The clearance, it depends on the LMC, least material condition. The least material condition for the hole, the largest hole, that's right, which is 1.251. The least material condition for the shaft, the smaller shaft, 1.247. And also positive. And also positive. When you have the largest hole and smallest shaft, still you have a gap in between. In this case, what do you expect? Do you have what type of fit? Is it clearance fit? Is it forced fit? Or transition, sometimes like that, sometimes like that. We have always clearance. That's right. In both cases, we have a clearance. We got allowance positive and clearance positive. I will talk about fits later, guys, okay? Loose always, very good. Loose fit. Now, let us talk about fit, guys. The first type of fit, guys, is the clearance fit. The parts are toleranced such that the largest shaft is smaller than the smallest hole. The allowance is positive and greater than 0. The second type, interference fit. Sometimes the allowance positive, sometimes negative. The interference fit, the maximum clearance is always negative. The parts must always be forced together. The maximum clearance is always positive. That means the allowance may be positive, may be negative. The parts must always be forced together. The transition fit, sorry guys, the interference, we don't have space at all. I'm sorry. Interference, we don't have space at all. The clearance always negative. Yes. And in this case, guys, we need force or sometimes force with heat to fit parts together. The last one, the transition fit. The parts are tolerant such that the allowance is negative and maximum clearance is positive. The parts may be loose or forced together. This example, guys, as you see, we have here a pulley or a gear, and the gear held in shaft with a key. So we have a transition fit between the gear and the shaft. And here, guys, we have bushing between the shaft and the mount. Between the bushing and the mount, interference to fit the bushing in the mount directly and keep them fixed together. Between the shaft and the bushing, we have clearance fit to let the shaft rotate easily. Again, clearance fit. The parts are turned such that largest shaft is smaller than smallest hole. Allowance is positive. In this example, guys, as you see, we have shaft, we have hole. The largest shaft is smallest than the hole always. We have a gap here and here, as you see. Even the maximum hole, the minimum shaft, still we have a gap. This is a clearance fit. Now, in general, guys, how we can calculate? Again, if you want to calculate the maximum clearance, this is example. We have a hole with dimensions and limits. We have a shaft with dimensions and limits. Now, guys, the maximum, let us start by the allowance. Allowance, it depends on the MMC condition, maximum material condition. So it is the MMC hole minus the MMC shaft. The maximum material condition for the hole is the smallest hole, which is 0.5. The maximum material condition for the shaft, the largest shaft, which is 0.503. Sorry, maximum for the shaft, it is 0.53, yes. I'm sorry, this is the shaft, sorry. So it is 0.498, 0.498, 0.5 minus 0.498, 0.002 positive. Now, to calculate the clearance, the maximum clearance, we need the LMC hole minus the LMC shaft. The LMC hole, the least material condition for the hole, which is the smallest hole, the largest hole, which is 0.503, minus the least material condition for the shaft, which is the smallest shaft, 0.495. The value is positive. When you have the clearance positive and the allowance positive, what we have? What type of fit we have, guys? Clearance fit? Yes, clearance fit. Yes, clearance. We have always positive clearance. Interference fit, or sometimes called force fit or shrink fit. Interference fit has limits of size that always result in interference between the mating parts. This example. Allowance, calculated, negative. Clearance, negative. That means what? Interference. You don't have a gap, and you have to force the shaft inside the hole. The transition fit, guys, transition fit may be either clearance or interference fit. That is, shaft may be either larger or smaller than the hole in the mating part. In this example, clearance positive, but the allowance negative. What that means? Sometimes if you pick one part, measure the dimension, sometimes it will be forced fit, sometimes will be clearance fit. So this is transition fit. Okay? This is example. Given diameter of a shaft 1.5 millimeter, upper limit 0.03, lower limit 0.04. For the hole, guys, basic size 1.48, upper limit 0.03, lower limit 0.05. Okay? My question, guys, how much the tolerance of the shaft?
Plus minus 0.0.
Tolerance for the shaft, how much? It is 0.07. Tolerance for the shaft. You have 0.03 positive and 0.04 negative. Positive minus negative give you addition. So you have 0.07 millimeter. What is the tolerance for the hole, guys? It's 0.08. Okay. What is the largest material condition for the shaft?
1.54.
It's the basic size plus 0.03 millimeter. What is the least material condition for the shaft? 1.5 minus 0.04. What is the MMC condition for the hole, guys? It's the basic size 1.48 minus 0.05, because the maximum material condition is the smallest hole. What is the LMC condition for the hole? It's the basic size plus 0.03 millimeter. Now, as you see, to calculate the allowance, you need MMC hole minus MMC shaft. We have negative value. Clearance, LMC hole minus LMC shaft, positive. One of them negative, one of them positive. What meant by that, guys? When you have negative, positive, transition. Now, guys, this is class activity. The first thing, we have to calculate the allowance for each. Calculate the maximum clearance, then indicate type of fit for these three assemblies. All right, guys, you can do it. Now, guys, listen. Take this one. The left one. Okay.
MMC hole.
Yes.
MMC shaft.
How much? MMC of the hole.
Plus 0.0.
It is the smallest hole, which is 50.
No, the bigger hole. Minus
No. You said MMC, that's right? MMC, the smallest hole, which is, see, 50 minus 50.1
0.1. Minus 0.
minus 50.05 minus 50.08, also negative. So we have both of them negative. What that means? Force fit or interference fit. Very good. The second one, 49.95 minus 50, negative. 50.05 minus 49.9, positive. So you have positive, negative, transition. Very good. The last one, 50 minus 49.5, positive. 50.05 minus 49.95 positive. So both of them positive clearance fit. So the left one shrink fit or forced fit. Okay, second one transition fit, and last one clearance fit. Now how we can create these things or these tolerances and write the values on Inventor. Yes.